Welcome! Earlier this week I gave a lecture to the Scottish Rite group in Washington DC about predicting the unpredictable. Basically the talk was about how difficult it is to predict the solar cycle. As most of you know, the sun goes through an 11-year sunspot cycle. These images, by the way, are in ultraviolet light taken exactly 1 year apart. And in ultraviolet, sunspots appear bright rather than dark. You can see here back in 1996, the sun had almost no features on it. Over the next 4 years, the number of sunspots increased till we had a maximum in the year 2001. After that, the sunspot numbers died away, and by 2006 we were almost back to where we were before, and by 2007 the sun was basically blank. So that's the sunspot cycle. And if we know it's 11 years, what's the big problem about predicting it? Well, let's see. Why should we even bother with trying to predict what the sun is going to do? Well, for us astronomers this is quite important because the sun is sort of our Rosetta Stone of all other stars, and it's a relatively simple star. So if we can't really predict very much about what's going on the sun, having got so many observations and being so close to it, how can we possibly claim that we understand some of the more exotic stars that we can see much further away and have far less data and information about? Well, you can't. But there's a practical application for this too. I was in the aerospace industry for 40 years. I often got inquiries about how the sun was going to affect the orbits of various satellites. As the sun becomes more active, the Earth's atmosphere heats up and expands. That causes additional drag on satellites in low Earth orbit, and they come down sooner, which costs the aerospace industry a lot of money. Also, during times of high solar activity, such as during flares or geomagnetic storms, data quality and image quality can be degraded. It can mess up radio communications. For example, if you are flying from Washington DC to Beijing, if there's a major storm going on, you can't fly over the pole, which is the Great Circle route, which means you have to divert to, say, somewhere like Anchorage. That means airlines have to use more fuel, change out more crews, and you get a bunch of very unhappy and delayed passengers, which is not good for the airline industry. Also, radio hams like a little bit of solar activity, but they don't like the sun to be completely quiet or too active, because actually the sun can even blank out all radio communications for a while when you have a major flare. It can even mess up your golf game, and this is possibly the most important of all. If you're standing in the middle of a fairway and you get your little GPS machine out to tell you how far you are away from that pin, the problem is that if there's a major geomagnetic storm going on, those readings are very inaccurate. In order to predict the solar cycle, you better understand what sunspots are. This is a fairly typical sunspot with a size about twice that of the Earth. Sunspots are first and foremost magnetic, but the fields there are tremendously strong, 20,000 times stronger than the Earth's magnetic field. And that is something that needs to be explained. The large-scale magnetic field of the sun is actually quite weak. So how do you get very strong sunspots derived from a basically weak magnetic field? Sunspots appear dark because they're cooler. If you look around the edge of this sunspot, you see this sort of network. These are convection cells bringing energy from the solar interior. They're called granulation. The temperature of those are about 5,700 degrees Kelvin. The center of the sunspot is about 4,700 degrees Kelvin. And you cannot see those convection cells so clearly in the sunspot, and where you can see them, they're smaller and elongated. So it seems the presence of the magnetic field is inhibiting that flow of energy from the solar interior in the sunspot itself, and that's why it appears darker, because it's cooler. Now, if you could pick a sunspot off the sun and put it up in the sky, it would be brighter than any star or any planet that you can see, and it would actually probably be brighter than the moon, depending on its size. Why do they form? Where do we get magnetic fields on the sun? Well, first clue is the sun is hot, and therefore that would vaporize just about any material known to humankind. Not only that, it would take the atoms and start stripping some of the electrons off, and as the sun is mainly made up of hydrogen, what we have here is a plasma comprising mainly of protons and electrons with a few ions in it. So there you have all the elements of a dynamo. You have a rotating sun, which actually doesn't rotate uniformly, and you have charged particles, and so charged particles moving is called an electric current. An electric current in certain circumstances can generate a magnetic field. So we have all the elements there to be able to produce a strong magnetic field. But why do the number of sunspots vary? If the solar rotation has anything to do with the generation of sunspots, the rotation is constant, at least from place to place. So if the rotation is constant, then they should be generating the same number of spots all the time. But that's not the case. There are other mysteries that we need to explain as part of understanding what sunspots are. When a sunspot group emerges like the one we see here, a large spot like this will appear at the lead of the region, and generally behind there'll be a scattering of smaller, weaker spots of the opposite polarity. And that group is generally tilted slightly towards the equator, with the large spot being closer to the equator than the trailing spots. Also, during the solar cycle, the large-scale field reverses. It starts off with one polarity, and at the end of the sunspot cycle, it's the opposite polarity. Therefore, the magnetic cycle of the sun is 22 years, whereas the sunspot cycle is on average 11 years. Halfway through that sunspot cycle, the polar fields almost completely disappear. We have to explain how that happens and why that happens on an approximately 11-year periodicity. In order to be able to explain and predict the solar cycle, we have to have a model that explains all of those things. And we actually have one. It's called the alpha-omega model. We'll start in the top left here with the sun at solar minimum, and at that time we'll say that the top of the sun is at north magnetic polarity and the bottom of the sun is south magnetic polarity, so the field lines run from north to south. That's called a poloidal field. But as I said, the sun rotates differentially, i.e. different speeds in different places. It rotates faster at the equator than it does at the pole, so after one rotation all of those field lines are bent to the west, i.e. to the right. It's 2 rotations, it's bent twice as much, 3 rotations, and so on. After years of such rotation, you get the magnetic field of the sun wound up in the way shown here on the top right. So the field lines have gone from north-south to east-west. That's called a toroidal field. Now, the way that those field lines are slanted explains why sunspot regions, when they emerge, are tilted towards the equator, oppositely in both hemispheres. It also explains how we've got a much stronger magnetic field. This winding up process actually strengthens the magnetic field. It's like one of those model airplanes you used to have when you were a kid, with a large propeller and a rubber band going from the propeller back to the tail, and you would wind up the propeller until you got the rubber band completely wound up as much as you can, release the propeller, release the plane, and the plane flies off into a tree and you never see it again. That process of winding up the rubber band is storing energy into it. And that's exactly what we're doing with the magnetic field, storing energy into it, making it stronger by winding it up. What happens though when you overwind a rubber band? It produces a little kink like you see in the bottom left corner here. The kink will have opposite polarities in the two hemispheres. Where in the northern hemisphere, with the current magnetic orientation we've got, the leading spot will be north polarity, the following spot will be south polarity, and the opposite in the other hemisphere. Now what you have here is 2 sets of sunspots which are both very, very strong, close together, and the chances are they're going to interact and start cancelling one another. That's called a flare. When that happens, it leaves the trailing regions as a residual field. You have a residual south field in the northern hemisphere and a residual north field in the southern hemisphere. And those fields, those residual fields, are transported slowly towards the poles, where they start cancelling the large-scale weak field. So by the time you get to solar maximum, most of that polar field has completely gone. But you've still got a lot of sunspots you produce even after solar maximum. And that residual field starts building up the opposite polarity in the pole. By the end of your sunspot cycle, you have predominantly south polarity field at the top of the sun and north polarity field at the bottom, the exact opposite of what we started. So then another 11 years further on, you'll be back to where you were before. So that's why the magnetic cycle is twice as long as the sunspot cycle. So here we have a model that explains everything we wanted to know about sunspots. So let's use it to predict the solar cycle. Well, the first problem is that such a model would predict a uniform cycle. And so once you had the period and the amplitude, you could predict the solar cycle in perpetuity, rather like a pendulum. Unfortunately, that's not the case. If you look at the last 24 cycles, The peak of those cycles have varied from everything from 50 to 200 in sunspot number, and the variation almost seems random. However, some people say, well, okay, we don't have just one oscillator producing the 11-year cycle, we have more than one oscillator. And in fact, you can almost see that oscillator in the modulation of the solar cycles. If you blur your eyes and put a sine wave over it, you can sort of see that there's some modulation there. However, it doesn't quite work. This is the so-called Gleisberg cycle with an 88-year period. No matter how you move it around, it doesn't quite work at all. But then the response to that is, well, it's not just one extra cycle, it's lots of cycles all working together in series. And that's the equivalent of doing a Fourier analysis of this. And if you have enough Fourier components, you can precisely reproduce this pattern of sunspot numbers for the various cycles. Well, then you can take those Fourier components and project them forward 10 years, and you have a prediction for the next cycle. Unfortunately, that has never worked. Unfortunately, the amplitude is not the only problem, there's also a timing problem. If this is a caricature of a solar cycle, you measure the length of the cycle from minimum to minimum. And so you have the minimum on the left, then it's followed sometime in the future with a maximum, and then the minimum on the right. But the shortest cycle from minimum to minimum we've observed is 8 years. The longest cycle is 14 years. So you already have nearly a factor of 2 in the uncertainty of the timing of the peak of the cycle. And you can break it down further. You can look at the time from minimum to maximum, and then the time from that maximum back to the next minimum. Minimum to maximum has varied from 3 to 7 years, and from maximum back to minimum has varied from 4 to 10 years. So in principle, we could have a cycle for anything from 7 years to 17 years long. So now you don't only need a set of oscillators to produce the amplitude of the cycle, you'll need a different set of oscillators that change the phase of the cycle so you get longer and shorter periods for the solar cycles themselves. Well, let's see how this range of possibilities can quickly mess up your ability to predict the solar cycle. I've marked down here in red a 3-year rise cycle, one to the minimum number of 50 and one to the maximum number of 200. And then blue I've marked the equivalent for 7-year rises. And just for grins, let's put in the 4-year decay. Now that says anywhere in this grey area that I've marked here is a perfectly valid possibility for the solar cycle. And if you're at solar minimum in 2020, say, you have no idea which of those possibilities is going to happen. Now you can actually trace the initial onset of the next cycle and see which of these curves it's following, but there's not a great deal of difference between some of them, and so you really can't say where your maximum is going to be or what your period of your cycle is going to be. You very rapidly exceed the range of observed solar cycles. So anything beyond that point, i.e. about 2.5 to 3 years, you have no useful information about the solar cycle, at least based on the length and the amplitude of the cycle. We've known about the solar cycle for about 175 years, so once it was discovered, everybody wanted to try to forecast it. How can I put this diplomatically? After 175 years of trying, we have a record that is unblemished with success. Let's take the predictions for solar cycle 24. There are 108 published predictions of solar cycle 24. It used over a dozen different mathematical techniques, all of which are perfectly valid and all of which are perfectly well done. We got amplitude predictions from 0 to 250, and that's actually larger than the range of the previous 24 cycles that we've ever seen. So there's basically no useful information there either. By definition, with 108 guesses, and that's basically what they are as far as I'm concerned, some of them are going to get it right. So claiming to get the amplitude right is probably much a matter of dumb luck. 98% of them, i.e. only 2 groups, got within 6 months of predicting the maximum date. And both of those groups got the amplitude wrong. So, of 108 published predictions, none were correct. And it gets yet more complicated. It's a tale of 2 hemispheres. If you look at the Sun as the 2 separate hemispheres and see which one is more dominant in producing sunspots, then you get the picture looking rather like this. Here red indicates the north is dominant, blue indicates the south is dominant. Now of course, according to that alpha omega model, those 2 should be symmetric. But for the last 5 cycles, the northern hemisphere has kicked off the process and the southern hemisphere has finished the process. So now If you were going to try to model this cycle with a bunch of oscillators in series, then you would have to have one set for the southern hemisphere and one set for the northern hemisphere, but vaguely coordinated with one another because they are producing sunspots at basically the same time. This makes your problem very much more difficult. What we need is some combination of oscillators that produce a cycle that is seemingly unpredictable. In this circumstance, I rather like the quote of Kerry Thornley: "What we imagine is order is merely the prevailing form of chaos." There's another one by Terry Pratchett which says that our confusion now is on a much higher plane. We have apparently chaotic behavior in both amplitude and timing of the cycles. So we need to generate some form of chaos from an ordered system. The sun is an ordered system, but it's producing what appears to be chaotic behavior. Is there such a system? Well, yes, there is. For example, you could consider the pendulum, but not a single pendulum, a dual pendulum. You have two pendulums, one at one length L1 and the other at L2, but the second one runs off the first pendulum. And so you can get what appears to be random behavior from such a system. Let me show you. Here's the pendulum system, and I want you to keep an eye on this particular part of the pendulum. See how far it swings from left to right. Now this is a computer simulation. And initially the pendulum just seems to act as though it's a pendulum with an L1 plus L2 length. But then things start to go wrong. You're still getting fairly long swings at the moment, but that's about to change. This gives every appearance of being random. From a simple ordered system of two pendulums, we've apparently produced a random pattern. If we were just observing the base of that pendulum and that represented the solar cycle, we would think that the things were random, and you'd have a mixture of long and short cycles, different period cycles, and different amplitude cycles. What I've done here is pick off the amplitude of the first few oscillations of this double pendulum. As I pointed out originally, the first four or so swings were approximately of uniform amplitude, but after that things go rather crazy. And if this was the amplitude of a solar cycle, it would fit in very well with some of the things we've seen in the 24 solar cycles that we've had to date. So there seems to be some hope that we could use this sort of system to predict the solar cycle, because even though this apparently is random, if we know the characteristics of those two oscillators in there working off of one another, we can predict this pattern. Except for one slight thing. The pattern here is chaotic. So if I'd release that end pendulum a little bit higher or a little bit lower, this pattern would be completely different. And if there's any perturbation on the system during that process, that would change the pattern immediately. So this system is not very stable to perturbations, and there's lots of potential perturbations on the sun that would change its oscillation system. Unfortunately, the problem gets worse. If we look back before the 24 cycles that I've shown you to date, shown here in blue, we have about another 150 years worth of data. They're shown in red because the data is more sparse and the equipment used to get it is not as good as the subsequent data. However, it's fairly clear that for about a 70-year period, the so-called Maunder Minimum, the sun produced very few, if any, sunspots. Now, if you remember that alpha omega model, we have a problem now, because that can't explain what we're seeing here. Remember, the next cycle depended on the residual field left over from the previous cycle. So if the sun is producing no sunspots, there's no residual fields to go to the poles and produce a new cycle the next time around. So the alpha omega model, once into a Maunder Minimum, could never get out of it again. And there's a second problem here. The cycle just before the Maunder Minimum was actually quite a large cycle. So somehow this system just turned off, which doesn't seem very practical. It's as though if it were the pendulum, somebody reached in there and grabbed the pendulum at some point during its progress, held it for 70 years, released it, and it just went back to doing what it was before. So we have a double problem in this particular issue with the Maunder Minimum. That there's something else in our alpha omega model that we haven't got as yet that's preventing us from being able to predict or understand the Maunder Minimum. Well, is there any hope at all? Well, yes, there is. What we need somehow is to take a look inside the sun and see if we can get the nature of the oscillators that are producing the solar cycle and changing the solar cycle. There's something that's been developed over the last few decades called helioseismology. That's where you look at the vibrations of the sun and try to get a view of the interior, rather like you do with a seismograph when an earthquake goes on in the earth. What we have on the right here is a Dopplergram. It's an image of the velocities on the surface of the sun. In fact, you can actually see solar rotation here. On the left, the image is slightly darker, and that is material coming towards you. On the right, the image is slightly lighter, and that's material going away from you. So there's the solar rotation right there and then. But you see, superimposed upon that, there seems to be some sort of pattern of waves behind that. So what we've done here is we're going to remove that solar rotation, which we know the quantity for, and you end up with something looking rather like an orange. But each one of those light and dark patches is a wave of different lengths. The shorter wavelengths sample the convective zone near the surface of the sun, and the longer wavelengths can penetrate deeper and deeper into the sun. So if you collect all the characteristics of those waves and how they change and how they vary, you get some idea of what's going on in the solar interior. In fact, you get images of the solar interior, which is rather spooky. This is one of the first images taken of the solar interior. This is an image of its rotational velocity. And as you can see, as I said before, at the surface, the sun is rotating faster than at the poles. But as you go deeper inside the sun is rotating slower. But you can use things like this, and as we get more detailed, we should be able to find some of the characteristics of what's changing in the solar interior. However, one of the things to note is that this is a global image at the moment, and so the two hemispheres are considered or assumed to be symmetric, and we've already found out that that's not the case. So there's still quite a long way to go, but I think this is the beginning of where we will eventually end up with predicting the solar cycle. So let's see if we can come to some conclusions about all of this. To date, nobody has managed to consistently predict the solar cycle. Every previous method, no matter how complicated or how sophisticated, has failed eventually. We've been looking at multiple coupled oscillators, but we only see the result, not each component, and we need to see those components enabled to produce a prediction of the solar cycle that's likely to be accurate. We have shown that you can get what is apparently chaotic from what is an ordered system. That chaotic system is actually predictable, but you need to understand what the various components of the systems are in order to be able to use that prediction. In helioseismology, maybe provide a way to get the answer finally, but we've still got a long way to go. So I hope you enjoyed this. Please pass it on to anybody you think might be finding it useful. And so until next time, goodbye.